Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. In the previous class, we have discussed about tension field beams, and also we have discussed that how the tension field action is going to be, and again tension field beams are subclassified into complete tension field beams and incomplete tension field beams. So today in this session, we are going to cover the topic incomplete tension field beams. So basically in the previous class we have seen tension field beams. Now when it comes to the incomplete tension field beams, so the plates, whenever the loads are applied and even near failure, they retain some capacity to hold, so that somewhere, that means somewhere in they will be in the state of tension as well as compression. So therefore it is very important to study the incomplete tension field beams. The learning outcomes in this module are students are able to determine the loads and stresses in incomplete tension field beams, and probably the following that we are going to even analyze for the post buckling behavior of the thin plates. So the plates they retain even after buckling, and they have some of their ability to support the loads even near failure. So therefore they are in a state of stress somewhere between the pure diagonal tension and the pre-buckling stress, and therefore such kind of a beam we regard it as incomplete tension field beam, because they will be in a state of stress somewhere between the pure diagonal tension as well as the pre-buckling stress. And usually these kind of incomplete tension field beams, evaluation of stresses and all, so usually this will be dealt by semi-empirical theories. And so here in this module we are going to present the semi-empirical theories for knowing the incomplete tension field beams. So firstly, it is assumed that the nominal web shear, that is tau, is taken as S by TD, that is shear force by the area, which is nothing but thickness of the wall and also depth. And usually this web shear, that is tau, it is divided into two components. One is a true shear component and the second one is a diagonal tension component. So two components, one is the true shear component and other one is the diagonal tension component, and then we write what is a true shear component and what is a diagonal tension component. So the diagonal tension component, now if you look at it here, the true shear component is written as tau s, that is equals to 1 minus k into tau, where k is called as the diagonal tension factor, and which is usually defined as it is a measure of the degree to which the diagonal tension is developed. So we are writing the diagonal tension, that is the shear component, as 1 minus k into tau. Similarly, the diagonal tension stress, we are writing it as k into tau. Okay, so 1 minus k into tau is the true shear component, and k into tau we are considering it as the diagonal tension stress. Now, so the value of k corresponding to a web having a critical shear stress, that is tau critical, is given by the empirical expression, and that is given as the value of k equals to tan h of, that is hyperbolic, into 0.5 log tau by tau critical. So this tau by tau critical, that is the shear stress at any point divided by the critical shear stress. So usually it is defined as the loading ratio or the buckling ratio. So therefore the constant, that is the buckling, that is the diagonal tension factor k, is defined as the measure of the degree to which the diagonal tension has developed, and again it is given by k equals to tan h of 0.5 log tau by tau critical. So here in this formula we are able to see tau critical, that is a critical shear stress in the denominator, and this critical shear stress may be calculated from the formula, and that is given by tau critical, that is elastic, that is equals to kss into E into T by B whole square into RD plus half into RB minus RD into B minus D whole cube, where KSS is nothing but the coefficient for the plate with simply supported edges, and where we have RD and RB are the empirical restraint coefficients for the vertical as well as the horizontal edges of the web panel respectively. So now here, earlier in the tension field beams, we have found out the formulas for the that is stress in the flanges as well as the stress in the web, and so those formulas are going to be modified by considering the diagonal tension factor, that is K into effect, and the stress equations are modified in the light of these assumptions and maybe rewritten in terms of the applied shear stress tau as. So we are going to rewrite this the flange, there is stress in the flange, that is nothing but Kt into cot alpha divided by 2 into AF by TD plus 0.5 into 1 minus K. So this is a stress in the flange, or else we can consider it as already we have discussed, that is the true shear. It is the diagonal tension shear is going to be divided into two components, that is a web shear, and it is divided into one is the component is nothing but true shear component, and another one is a diagonal tension component. So now here this is the stress what we got, and another stress, that is sigma s, that is equal to Kt tan alpha divided by As into As divided by Tb plus 0.5 into 1 minus K. So these are the stresses that will arise whenever we try to study about the incomplete tension field beams. So complete tension field beams, wherever we got the formula and we use the relationships from the diagram which we consider the cantilever beam, and in which the load is acting, that is nothing but W, and we consider the angle of diagonal tension alpha, and then we derived the formulas for the stress in the flange and then the stress in the web as well as the other stresses. So now when it comes to the incomplete tension field beams, we have to understand that those are, here we are not going to follow the procedure of complete tension field beam, but here we are going to follow the procedure of semi-empirical relationships, because the prediction of incomplete tension field beams is much more difficult than the complete tension field beams, and mostly they rely on the empirical relationships. So the next one what we are going to see here, it is the post buckling behavior. Now this post buckling behavior is very, very important, because when you try to see the stress strain curve for example, let's consider the stress strain curve for mild steel. So you're going to get a curve like this, and in which you will plot stress versus strain curve for mild steel, and you can see here clearly, up to here you can consider as elastic zone, and after that you can consider it as plastic zone. Now whatever we study the tension field beams, and when it comes to the post buckling behavior, so usually they deal with this area, that is the plastic zone. Okay, so the calculation of whatever you are calculating the parameters and is going to be much more difficult, and usually they are not linear, because it is a non-linear analysis what we are going to study here. So therefore the post buckling behavior is very, very important for every engineer to understand, because we know we study up to the buckling process, but after buckling, what's happening in the material, what's happening to the material, and is it safe to again add some more loads to it, and if it is safe, how far it can be safe to sustain the loads that we apply after the buckling has occurred. So that is very, very important phenomena to understand, and it is a very critical phenomena also. So theoretically it is rather practically you get more exposure than the theoretical work, but let's try to understand theoretically here the post buckling behavior. So what happens here, till elastic zone the stresses and strains are usually uniform and linear, and after that elastic zone and the stresses and strains, and those are not going to be not uniform and not linear as well. So you can clearly observe after this elastic zone, and the curve is going to decline like this, and then you're going to get the failure point at this point. So till there is a point called strain hardening. So in this region, even if you add small amounts of stress and it's going to be give large amounts of strain. So there's a very important parameter that we have to understand through this diagram. So now what happens here, after buckling, you can see here the beam flanges are relatively light. The beam flanges are relatively light for failure due to yielding to occur in the beam flanges after the web has buckled. So this is very important, that is after the web has buckled, so that the plastic hinges form and the failure mechanism of the type is shown in the figure that is exists. So what happens here? So after buckling, what happens? You will find the plastic hinges. Okay, where are the plastic hinges in the diagram? So you can see here X is one plastic hinge, Y is another plastic hinge, and W is another plastic hinge, and Z is another plastic hinge. So these hinges will form, and you can clearly observe the diagram also, and the direction of the buckle. So this is the direction of the buckle which you are able to see, that is the direction of the buckle, and this is a normal rectangular portion. So after buckling, now it has got a particular shape that is shown in this figure, and you can see the plastic hinges that are formed, and so this is the usual depth of that whatever the element you consider. So now that is going to be changed to a pattern like this along with the plastic hinges. So for this kind of diagram, and if you look at this diagram, and if you consider one panel that is collapsed due to a shear load S and bending moment M, and you can see the panel is nothing but A, X and B, Z. That is a panel which we have seen, and that panel has been collapsed. So therefore, for that panel, and if you consider shear force as S and bending moment as M, and the plastic hinges are formed at W, X, Y, Z as we have seen in the diagram. So in the initial stages of the loading, the web remains perfectly flat until it reaches the critical stresses, that is the tau critical in shear and sigma critical in bending. So until the web will be perfectly flat until it reaches the critical values, that may be in the shear or that may be in the bending. So the value of the stresses may be found approximately using this formula, that is sigma mb by sigma crb whole square plus tau m by tau cr whole square, that is equal to 1, where sigma crb is a critical value of the bending stress with shear force equal to 0 and bending moment equal to 0, and tau critical, that is tau cr is nothing but the critical value of shear stress again when S equal to 0 and M equal to 0. Okay, so this is a post buckling behavior, and through this from this equation you can able to find out the stresses that are associated with the post buckling behavior. But as I mentioned, the post buckling behavior is a non-linear phenomena that we will see in the practical cases. So the practical orientation for this post buckling behavior need to be done. So it can be done using the softwares, that is ANSYS or any other softwares in which you can able to clearly calculate the values of the stresses after buckling. Okay, so that is very, very important. After buckling, how much load is going to be withstand and before that failure can occur in the material. So that is a post buckling behavior. So for instance, let's try to have a problem on this compressed tension field beams. So the question which is shown here, it is a cantilever beam, just like it is having like a tension field beam. So tension field beam, and in which a load is applied, that is 5 kilonewton load is applied, and clearly you can see that it's been comprised of a flanges as well as web. One is upper flange is there and one lower flange is there, and it is connected by thin web which is shown here. So let's look into this problem. So the beam shown in figure is assumed to have a complete tension field web if the cross-sectional areas of the flanges and the stiffeners are 350 mm square and 300 mm square, and the elastic section modulus of each flange is 750 mm cube. Determine the maximum stress in a flange and also whether or not the stiffeners will buckle. This is the question. We need to calculate the maximum stress in the flange and then we ensure that whether the stiffeners will buckle or not. So he has given the thickness of the web as 2 mm and moment of inertia, that is second moment of area of a stiffener about an axis, is given as 2000 mm per 4 and Young's modulus he has given as 70,000 Newton per mm square. So let's look into this problem to calculate the maximum stress of the flange. So we have a formula that we've seen in this one, that is tan to the power of 4 alpha that is equals to 1 plus TD by 2 AF. Okay. Divided by 1 plus TBAS. So we have the formula for the angle of diagonal tension, that is alpha, and in which formula you have tan for 4 alpha, that is equals to 1 plus TD by 2 into AF divided by 1 plus TB divided by AS, where TD is the thickness of the skin and AF is nothing but the area of the flange and AS is nothing but the area of the stiffener. So as we have known the formula, then let's try to substitute. Tan power 4 alpha, that is equal to 1 plus thickness of the skin is taken as 2 and depth in the diagram, which you can see here, it has 400 and the 400 divided by again thickness is 2 and area of the flange that is mentioned in the question, that is 350 mm square divided by 1 plus again thickness is nothing but 2 mm and width of the panel that we have seen here, width of the panel is taken as 300 mm and then that you can add divided by area of the stiffener, that is also given as 300 mm in the question. And when you try to calculate, you are going to get tan power 4 alpha equals to 0.7143, so that you can find out the value of alpha, that is equals to 42.6 degrees. So first starting with the diagonal tension angle, that is alpha, which we need to calculate, and after that the maximum flange stress will occur in the top flange at the built-in end and where the bending moment on the beam is the greatest and the stresses due to bending and the diagonal tension are additive. So that's what is meant to say, that there is a cantilever beam and since he's asking to calculate the maximum stress in the flange, and we know that the maximum stress will occur at the fixed end, that is the built-in end, and so at that end the bending momentum will be maximum and you're going to get the stress maximum at that fixed end or the built-in end. So therefore, this formula which we already know, that the flange force, that is force in the top flange, that is given by WZ divided by D plus W by 2 tan alpha, that we can see from the derivation of the complete tension field beam. And now you are going to substitute and we got 5 Newton and the Z is nothing but the distance, 5 kilonewtons, and Z is nothing but any distance divided by the depth, that is nothing but 400 plus 5 divided by 2 into tan 42.6 degrees. So this is nothing but the force in the top flange. And if you look at into this one, you can consider this from here to here completely, you can consider as distance Z. Okay, so when you try to substitute in the formula, and you're going to get the force in the top flange as 17.7 kilonewton, and then the direct stress in the top flange produced by the externally applied bending moment and the diagonal tension is equals to what we are going to get is 17.7 into 103 by 350, that is equals to 50.7 Newton per mm square. So that is the direct stress in the top flange. We calculated the force in the top flange and then you calculating the direct stress, and we know the simple formula for calculating this, nothing but what sigma equals to m by I into y, so that you can substitute and you can get the value of the direct stress. Okay, and in addition to this uniform compressive stress, the local bending of the type that is shown in the figure occurs. So the local bending also occurs, and for that local bending So for the local bending moment in the top flange at the built-in end and is found by using the equation, that is Mmax equals to W B square into tan alpha by 12D, and we already know all these values. We know that W is 5 kilonewton, 5 into 10 power 3, and the width is 300, so 300 square into tan into alpha is about 42.6 degrees divided by 12D, that is 12 into 400 mm. So you're going to get the maximum bending moment, that is equals to 8.6 into 10 to the power of 4 Newton mm. So the maximum compressive stress corresponding to this bending moment occurs at the lower extremity of the flange, and you can calculate this, that is nothing but is equals to 8.6 into 104 by 750. Again, you can use a similar equation to find out this one. So 8.6 into 104 divided by 750, that is equals to 114.9 Newton per mm square. So this is the maximum compressive stress. Thus the maximum stress in the flange occurs on the inside of the top flange at the built-in end, because we have seen both top flange at the built-in end of the beam and is compressive and equal to, and if you try to add these two, and 114.9 plus 50.7, so total together you are going to get 165.6 Newton per mm square. That is a maximum stress that you're going to obtain from this. And similarly, if you try to find out the other loads, the compressive load in a stiffener is given by the formula, that is P equals to W B by D into tan alpha, and you can substitute W and you can substitute for B, that is 300, and then tan alpha is nothing but tan into 42.6 degrees divided by depth is 400. So you're going to get the compressive load in the stiffener, that is P equals to 3.4 kilonewton. And we have the condition also, equivalent lengths when width is less than 1 point times depth. If you have a condition like this, the equivalent length is given by LE equals to D divided by under root 4 minus 2 into B by D. And if the width is greater than 1.5 times depth, then the equivalent length can be considered as depth itself directly. So let's try to find out, because the equivalent length, so also the width is less than the 1.5 times the depth. So you have to follow the first condition in which you have the formula, this one. So therefore the calculation of equivalent length LE equals to 400, the formula we have here, depth D by under root 4 minus 2 into B by D. So 400 divided by under root 4 minus 2 into B by D, that is 300 divided by 400, that you are going to get 253 mm, that is the equivalent length. And once you get the equivalent length, you can find out the critical load using the formula, which is nothing but pi square EI by L equivalent square, LE square. Okay, so pi square E is the Young's modulus that is given in the question, which is given as 70,000 Newton per mm square, and even he has given the moment of inertia also as 2000 mm power 4. So let's try to substitute this pi square into 70,000 into 2000 divided by that is equivalent length, that is 253 square, and we are going to get the critical load, that is 22 kilonewton. Okay, so this shows that is the critical load, and which shows that clearly the stiffener will not buckle. Okay, so if because you're going to apply the load here, from this condition you've seen that the maximum stress that you have seen is nothing but 165.6 Newton per mm square. Okay, and so yeah, so you've seen here the top flange, that is in the top flange itself you have the load, that is nothing but 17.7, and even you will have the load in the bottom flange also. So even if you see the top flange and bottom flange, both the loads also, so when you compare with the critical load is just 22 kilonewton. So it is more than that by comparing with the top flange and the bottom flange loads. So therefore it is within the limits only, so therefore the stiffeners will not buckle according to the problem which is given. Okay, so that's all from today's class. Let's try to continue our session in the next class by the subject called, that is topic called. So that's it. So in the next class we are going to see unsymmetrical bending of the beams. Thank you everyone for watching.